Yeah, dear all, we'll start with the stepper motor interface. What's a stepper motor? A stepper motor is a electromechanical device which rotates in a particular step. You have got many applications of the stepper motor. It could be used even in the robotic applications, or it could be used where you have to have a particular angle of movement, right? And then we go in for using the stepper motor. So initially we'll discuss on the working principle of stepper motor, and then we'll go ahead with the programming. Here goes the construction of the stepper motor. As we can see here, it consists of the center, which is known as the rotor, which keeps rotating, and it has got the stator. So the rotor and the stator are made up of the magnets, and the rotor is consisting of a magnetic coil internally, and the stator has a magnet over which a coil is being wound. So what happens here is when you apply the current, like for example, these are the four rotors as we can see over here. One end of the coil would be connected to the ground, while the other end would be taken as the inputs that have to be provided. So let's assume that all the rotor which are being coiled with the electric coil are connected to ground, while the other end have the inputs say as A, B, C and D. The moment you apply a value of 1 to this particular rotor, then there is a flow of current that takes place from the high intensity to low intensity. While the others, that is this coil B, C and D, there is no current that flows. Hence there is a maximum electric flux that's being generated around this coil, and the internal rotor would rotate and align itself towards A. Next, we apply the current, voltage to this coil B, while the rest of them are set with a value of 0, 0. Then we observe that there is a maximum electric flux applied, or the flux being generated around this coil B, and hence the internal rotor would move. As you can see in the diagram over here, the applications, and we see that there is a movement of internal rotor that takes place. So in this way, the internal rotor starts rotating on the application of the voltage, right, to the stator externally. Now the most important concept here goes is a step angle. As we can see here, there are the two teeth, and between the two is what we know as the step angle. So what is step angle? It's a minimum degree of rotation with a single step that's required for us, because in order to calculate how many rotations the stepper motor has to rotate, or how many steps, what angle it has to rotate, we need to know what is the step angle. So the number of steps per revolution is given by 360 degrees by step angle. What is 360? It's a complete one complete rotation. Obviously it would be 360 divided by step angle. Normally the stepper motors come with a step angle of 1.8 degrees or with the 2 degrees. So the step per second would be calculated as RPM, that is the steps per revolution, that is the total rotation that goes into the steps per revolution divided by 60 degrees. So by this we'll come to know what is the step per second. Then for example, if you say that the step angle is 2 degrees, that means what you can see that between the two teeth, if it is 2 degrees, then we know that 360 degree is one complete rotations divided by 2 degree would come out to be 180 degrees. Now why this concept is important here is, say for example you have given a problem statement to say that it has to rotate say for only 90 degrees, or it has to rotate for 45 degrees, or it has to rotate for some 180 degrees. Then by knowing the step angle, you can find out how many steps are required for the motor to rotate for the given angle. So the next is, as we have seen in the discussion of the working principle, that stator whatever you have, right, you provide a particular sequence of input such that there is an electromagnetic flux that's being generated, and hence the internal rotor stator rather will start rotating. So let's go with the step sequence that is required. The stepper motor has got two way of generating the step sequence. So either it is two phase on or it is one phase on. So what is meant by two phase on? It means that two of the coils are being activated. Alright, as seen in the previous diagram over there, we have four different coils, that is A, B, C and D. So whenever we apply the voltage to the coil A and to the coil B, so let us quickly go back here. Let us take this to be as A, right? This to be as B, C and D, right? So when A and D are being applied with the value of 1 and 1, so where is the maximum electric flux is in this direction. So obviously the internal stator would move, the rotor would move along this particular path. Next, we activate the coil A and B. Then when we activate the coil A and B, then we have the maximum electric flux being generated in between the coil, and hence the internal rotor would rotate. Then next goes the sequence of B and C, and then goes the sequence of C and D. Fine. So this is how you generate the step sequence, which is two phase on. So in the clockwise, it goes with the sequence of 9, C, 6 and 3, and in the anti-clockwise or the counterclockwise, it is 3, 6, C and 9. The sequence can start from anywhere, but you need to follow the sequence later on. The next is the one phase on, and we say here it to be as a full step. The full step in the sense, in between the two movements, it's a complete 1.8 degrees, or it could be the 2 degrees movement that happens, and hence it's known as the full step. When we say it to be as one phase on, it is that only one coil is being provided with the voltage. The activation takes place in that particular coil, while rest of all the coils there won't be any electromagnetic flux being generated, and hence the internal rotor will rotate along the direction of the coil A. Next is we energize the coil B by sending a value of 1. So whatever we have written here as 1, 0, 0 or 0, 1, 0, these are the logical sequences that are being provided. But effectively when we look at the electrical parameters, it would be the voltage of 0 or the 5 volts that's being applied to the respective coils. Like for example, if you say the sequence is 0, 1, 0, 0, effectively we are applying a voltage of 0 to coil A, 5 volts to the coil B, and 0 volts again to C, and 0 volts to D. So the internal rotor would again align itself to the coil of B. Next, when C is energized, it moves along C. When D is energized, it moves along D. So you see that the step sequence of 8, 4, 2 and 1 will make the stepper motor rotate in the clockwise direction. On the other hand, when we give the sequence as 1, 2, 4 and 8, it makes the motor rotate in the anti-clockwise direction. So the full step, as I said, would make the internal rotor rotate for the complete step angle of 1.80 degrees or 2 degrees, depending upon the construction of the stepper motor for a particular step angle. We also have the other sequence as the half step, right? So half step in the sense wherein we activate the coil such that the movement of the coil takes place by 0.9 degrees or 2 degrees. That's known as the half step. That happens with a combination of with the combination of one phase on and a two phase on. So when you make one phase on, then two phase on, again one phase on, two phase on, will generate the half step sequence. This is the interfacing diagram that we have for the stepper motor. As we can see, the motor this is the driver circuitry that goes with the stepper motor, wherein the coils, right, A, B, C, D, are being connected through the diode, and the other end of the diode is connected to 5 volts. Here is the connector, or what is known as the power mat, and this in turn you have the socket. From here we make the connections to the stepper motor. As usual, we'll be using the ULN 2803 high current, high voltage driver IC, wherein the output from the LPC1768 pins, that is P2.0 to 2.3, are connected to your coil inputs as A, B, C and D. That comes from PC4, 5, 6 and 7. Through this driver IC, it goes to the output, that is A, B and C. This in turn is connected to the internal driver of circuitry of the stepper motor. So when you provide the input sequence as 1, 0, 0, 0, what happens to this motor internally? It gets negated and then makes the motor rotate in the clockwise direction. Next, you give it as 0, 1, 0, 0. Again, it performs the operations. So in this particular discussion, we'll be using one phase on for writing the program. So let's see how the program goes with it. The problem statement is: write an ARM embedded C program to rotate the stepper motor clockwise one complete rotation and anti-clockwise one complete rotation. What we mean by one complete rotation is one complete, a total of 360 degrees. If you start from one point, it completes one rotation which is equal to 360 degrees, and it's in both the direction, that is clockwise as well as anti-clockwise. So the logic of the program is pretty simple enough. We need to make P2.0 as well as up to 2.3 as the output pins. Then you give the test sequence of the motor as 8, 4, 2 and 1, which makes the motor rotate in the clockwise, and you inverse the sequence. We'll be seeing that it rotates in the anti-clockwise direction. Logic is: configure the port pins P2.0 to 2.3 as output. Next is the step sequence considered here is one phase on, hence it's 8, 4, 2, 1, which makes the motor rotate in the clockwise. 1, 2, 4, 8 makes the motor rotate in the anti-clockwise direction. And between the sequence, right, into in its one step, hence all the 4 sequence will correspond to 4 steps. As we know that whenever there is a movement, right, you give the sequence. Between the sequences, that is between 8 and 4, it's a movement of one step. Next, between 4 and 2, there is another step that moves. Between 2 and 1, there is another movement, and 1 and 8, there is another movement. So once you give all the 4 sequences to the stepper motor, it will rotate by 4 steps. So this is very important because we are going to put it in a loop. So the calculation of the number of steps will depend upon these sequences that are being provided. So let's understand the program. The first statement is hash include LPC1768, the header file being included. Then we have used two functions. One is the clockwise and another one is the anti-clockwise. So you have the function declaration being done, or the prototype declaration being done. And we'll be using these variables as var1 and var2 long int, because we have a complete 32-bit data being put into that. We would also require these variables as I, j and k internally for the delay generations and so on. So the variables can always be declared later depending upon number of variables being used in our program. Let's begin with the main program. The first statements that we see are the initialization statement that goes. So for P 2.0 to 2.3, we require the pin select 4 being used, and since all have to be programmed as the GPIO, we have set it with the value of 00. And next is the FIO DIR register, direction register. So all the lower 4 bits have to be made as 1, because all the 4 bits, that is P0 2.0 to 2.3, are being made as the output. Right. Now the most important is this for loop that goes. For j equal to 0, j less than 50. Let us see the complete main program, then we'll go with the discussion. Yeah. What is done here is we will initialize a counter and then call the function that is clockwise. This is the delay between the clockwise and the anti-clockwise, so that when it switches over, there is some amount of time, or the time that's being provided for the motor to switch on, because it's an electromechanical system, so you cannot expect it to be rotating very instantaneously. So you have to provide some amount of delay so that there is a proper energy that is being generated, that's an electromagnetic flux being generated internally into the stepper motor, and you can see that the motor rotates properly in the clockwise or anti-clockwise direction. Now why have we taken the value 50 over here? Okay, why is that we have taken a value 50 and then called as the clockwise? Similarly, we have taken value 50 over here and called the anti-clockwise direction. Just put a thought on this. We will come back to why this value is 50. So we have initialized j equal to 0 up to 50, and then we call the function that is clockwise. Then we call this as a delay, so that the switching between the clock and anti-clockwise is done properly. And then we again put it to be with the 50, and then we call the anti-clockwise again. So let's understand the clockwise and the anti-clockwise programs. Clockwise, the variable taken here is to be as VAR01. Now this is the input, which is 1, which means it is nibble wise, it is 0, 0, 1. For I equal to 0, I less than 3. What are we doing in this program here is, in this particular function, we are generating all the 4 steps. Okay, how do we generate all the 4 steps? Initially, we are sending a value of 1, 1, so that if at all there is any bit sequence or any energy, right, electroflux that's being generated into the stepper motor, it's all nullified. So you send the first sequence of 0001. I'm talking about the binary sequence, right? Through this VR variable into FIO set. So only the coil A would be activated and then it rotates. Now we have put it left shift in the clockwise. Effectively it has to be a right shift. Why? Because it's basically with the arrangement, if you recollect, the diodes are being connected to a value of 1, which means that you have to provide a inverse input from ABC such that the motor rotates, right? Because effectively if you see at the arrangement, the diode, the anode and the cathode, right, the anode should be with the value of 1 and the cathode should be 0, but the internal arrangement is in the opposite directions. So here by providing a value of 0 and 1, we make it rotate in the clockwise direction. So we shift that value 1 to the left, and again the increment the counter I, it becomes 1. Then you send the sequence, then you increment the value of I, it becomes 2, as well as you're shifting, then the next coil is being made as 1, and this whole process repeats. As you can see here, in between the step sequence also we are calling a delay. Now this delay is being called so that between the steps there is sufficient time for the motor to stabilize, and then the next coil will get energized. Now looking at the anti-clockwise program, it's very similar to clockwise, only the difference that lies is you'll be shifting it right once. So instead of making it move with a sequence of 1, 8, 4, 2 and so on, we start with 8. So the initial value that's being loaded is with a value of 8, which corresponds to 1 0 0 0. Then next you shift it right, it becomes 4 0 0 2 0 0 and 1. I said you may feel that in the theory discussion we have said that clockwise is the right shift and anti-clockwise is left shift. Now it's being taken opposite because the board that we have requires this type of the arrangement, because the diode is connected the other way out. It's not the normal connection of the diode that happens. The cathodes are being connected to a value of 1, so obviously the anode should be with the value of 0 such that the energy is being generated and the coil makes movement. The observation between these two functions is, once either the clockwise is being executed or the anti-clockwise is executed, the internal motor will rotate for 4 steps. Remember, it will rotate for 4 steps. Now let me go back to the main program. We had just put a query as to why we have written 50 over here. Is there any specific reason? Yes. We saw that the clockwise and the anti-clockwise will generate 4 steps. Fine. And what is the problem statement? The problem statement says that the motor has to rotate for 360 degrees. So for 360 degrees with the step angle of 1.8 degrees, how many steps are required? You require 200 steps, of which 4 steps are being generated in the clockwise as well as in the anti-clockwise function. Once a clockwise is being called, it will generate 4 steps, and hence we require this function to be called 50 times. So 50 into 4 will generate 200 steps. 200 into the step angle of 1.8 degrees will give us 360 degrees, and hence the motor will rotate for clockwise for 1 complete rotations and anti-clockwise for one other complete rotation. So very important is the value that goes into this particular for loop. It all depends upon what is the angle of rotation. For example, if you say that the motor has to rotate for say 180 degrees, right, and then stop. Then what is required? Instead of the value 50 here, you would reduce it to 25. Why? Because 25 into 4 will give us 100. So 100 steps corresponds to 180 degrees. Again, it depends upon the step angle. The step angle we have considered here is 1.80 degrees. So let us go into see how the program works on the actual hardware.
What you can see over here is the stepper motor interface. This is the driver IC, because LPC2148 GPIOs cannot drive the motor directly. So there has to be a circuit which provides sufficient amount of current for the motor to drive. So this whatever circuitry that you see over here is the driver circuitry. This is the driver IC that goes, and these are the connections to the motor. So the connections are associated with A, B, C and D. Those are the wires. And the last one we have here, you can see this white and black, right? So this is the wire which is connected to the ground, right? And the VDD connections. And these are the coil connections that go to the internal coil A, B, C, D. Fine. So this is a simple connections that we need to make. So let us download the program. So we have already browsed the stepper.x here, and then we start. The program is getting downloaded. Once it downloads, we can see that it rotates. You can see now it's rotating in the clockwise. So it completes one rotation. Yeah, and then it's moving in the anti-clockwise direction. So this process repeats unless and until you stop.
Okay, so we have seen how the motor rotates in the clockwise as well as the anti-clockwise with respect to the program that we have written. There can be many modifications to this program. As I said, it can be only for a particular step angle, for a particular angle of rotations, or it could be for a particular number of steps. So the main modification with respect to this program would mainly lie in the main program. The logic of the function, that is clockwise and anti-clockwise, remains the same, right? That's why we have written them as functions, not into the main program. What change that happens is only into the number of steps over here. I'll just quickly run through and I'll show you how it is. Yeah, so the value that whatever you give here as 50, it could be different. As I said, if it is for 90 degrees of rotation, then accordingly it would be what? 200 divided by 4, which will be 50, and further divided by 4 you get it in some points. So one step more or less is fine. So this is almost the program which can be used with small modifications into different step angle. If you want only clockwise, then do eliminate the program of the anti-clockwise. If you want only anti-clockwise, do eliminate calling the function in the clockwise. Hope this is clear to you, right? So just to conclude upon, we have understood the working principle of the stepper motor, the construction. We have learnt about what is the step sequence, one phase on, two phase on for a full step as well as a half step. And then we have also seen a program which is almost similar for different variations of the program to rotate the motor clockwise and anti-clockwise for one complete rotations. Thank you for your patience. In the next session, we will take up the program on interfacing the external interrupt. We'll see how we program LPC1768 for an interrupt. So we'll use a switch which will generate a signal as an interrupt to the LPC1768. Thank you.